Today, for the machine learning project, I have selected the hepatocellular carcinoma dataset, which is downloaded from UCI machine learning repositories. So I have downloaded this data in a zip format and loaded it in the R. So this data frame consists of an 164 observations of 50 variables, and all these variables consist of an all three types of data, all three types of a column type. They like they include the categorical variable, the ordinal variable, and also the continuous variable. So that is one of the main reasons I have selected this dataset. So this dataset is about a survival rate of a patient who was diagnosed with a hepatocellular carcinoma, considering all these other factors which are called as a predictors. So for today, we are developing models to predict the survival rate of a patient based on all these available data. For easy exploration, I have made this plot, box plot, with three different y limiters because you, my dataset consists of a vast range of values, so I couldn't concise everything into one graph. So I've made it with three different y limiters, and you can see the outliers very clearly. And for the exploration of the dataset, I have made this correlation matrix with the dark blue one being the strong correlation and red being not so correlated. And my dataset is not showing any significant correlation between any two variables. And I think that's a good thing considering a dataset. And so that's how I explored the dataset. And for the pre-processing of the dataset, I have initially I you can see the dataset has a lot of NA values. Particularly, it has a lot of NA values in an individual columns. So before imputing the NA values, and I don't want to remove the NA values, so I have decided to keep the columns that have a NA value percentage less than 15, sorry, 15, because when it goes beyond 15, I think the data is biased when you impute it with mean or median. So that's why I have removed those columns, and I have used the library mice for data imputation. And I have normalized the data by using the min-max normalization method, and I have normalized all the continuous variables. And for the dummy coding, so for the ordinal variables, I have dummy coded them using a fast dummies library and dummy calls. So for the principal component analysis, I have used the prcomp function, and I have generated this plot which indicates the percentage of variance for each column. And this is another plot that is generated, which is kind of tough to explain. So anyways, for this variance plot is based upon the extent of invariance within a column, and based on the values that I have retrieved by this proportion of variance calculation, I have removed three columns because they lack that extent of a variation. It doesn't really much contribute for the modeling. So I have developed the four different types of models on the data sets that include like logistic regression, KNN, naive, and neural networks. I have developed models both on holdout method and k-fold validation method. The reason I have chosen KNN and naive is KNN, naive, and logistic regression is that because the predictor variable is a categorical variable, and I have thought like why not use another model from unsupervised machine learning, and I have decided to use neural networks to make the predictions. So I have divided the dataset into training and test dataset using the tools, a library, and a sample split function. I have divided 75% of the dataset as a training and remaining 25% as a test, and the division is a randomized division. I have developed all these models on the training data set. So for the logistic regression model, before developing a model, I have removed all the non-significant columns by using this backstep process, and only the significant columns I used to develop the model. This is a summary of the model. And for the naive-Bayes model, before applying a naive-Bayes model, I have binned all the continuous normalized dataset into four labels as 0, 1, 2, 3, because naive-Bayes function of this library performs better on a binned data set, and so hence I have binned it, and I have run the naive model on the data set, and then I have developed the KNN data set, and for the KNN data set, the K has been chosen as an 11 because I have around 160 data sets, and I can choose around 10 or 11, but I choose 11 because it's odd number and to avoid any is tie between the predictions. So for the neural networks, I have used hidden layers of 5 and developed the model. This is the plot of the neural network model. So I have used this holdout method and made predictions for the test dataset and developed a confusion matrix to calculate the accuracy for each of these models. And so for the LM model, the prediction accuracy is 65%, and for the naive Bayes, it's around 60%, and for the KNN, it's around 78%, and for the neural networks, accuracy is about 63%. And for the k-fold validation of the models, I have calculated the accuracy for the using a 10-fold CV model and calculated the accuracy rate for all these individual models by using this function called fold validation, and the accuracy levels for logistic regression is 68, for the naive is 65, KNN is 86, and for the neural it's 64. So based on this k-fold values, accuracy values, I have tuned the models, and by using the library caret and a train control, and I have trained the model for the dataset using the method, and then I have used the very same model on the test dataset that was created before and made a confusion matrix to compare the accuracies. And so this is the confusion matrix for the k-fold validation. With the k-fold validation tuned at 75, and this for the naive Bayes it's around 65, and KNN it's 70, and for the neural it's 95. And this is the plot that indicate the accuracy rate between the k-fold and holdout. All the red points include the k-fold, all the blue points include the holdout, and you can see there's a significant accuracy increase for the k-fold than compared to the holdout method. And for the comparison of the models, I have used this ROC curve that is developed for the performance of the individual models with the parameters sensitivity and specificity, and compared all the four models of a holdout method. In this graph, we can see that there's an increased sensitivity for the KNN, but the specificity is maximum for a neural. This is how we compare the holdout models, and for the CV models, I have plotted this box plot of an accuracy box plot. And I have also plotted a kappa plot for this 10-fold CV to compare between individual models of the 10 CV. And for the stacked ensemble model, I have trained the model by using a caret list, and I have by using a combination of all the four models, and I have developed a KNN model based on the model that was trained by using this caret list, and developed the accuracy and calculated the accuracy of the model, which is 71.55%, and this is the summary of the results that was created in the stack assemble.